Hey students! So it's been blizzarding up here at Tahoe. I'm at the base of the new site for the RJUHSD Ski Mountain, and we're checking out some stuff with the engineers. Anyway, I need you guys' help. First thing I gotta do is get these gloves on. It's hard to type here in the cold. But in the meantime, remind yourself each of these things. What's kinetic energy? What's gravitational potential energy? What's elastic potential energy? And what's thermal energy? And in each of these cases, I want you to think of an example. Give you like 30 seconds here while I grab some hot chocolate. And we'll see if we come up with some of the same examples or not. All right. So kinetic energy, I'm thinking of a skier moving really fast. It's a big object moving in an organized way. The fact that they have mass and velocity is what gives them kinetic energy. For potential energy, I'm thinking of a skier up at the very tippy top of a mountain. The fact that they're up high in Earth's gravitational field, that height and the location in the field is what's giving them their energy. As far as elastic potential energy, not thinking of a ski example so much, but when you guys were launching water rockets, that compressed air definitely counted. And then what's thermal energy? Well, that's something I'm missing out here in the cold. But thermal energy is basically small scale motion. It's disorganized, it's chaotic, it's otherwise just like kinetic energy though. Anyway, with that quick review here, let's get going. So what we're gonna do today is cover some ski lift energy concepts. You guys are gonna review what kinds of different forms energy takes and when. You're gonna make sure you're using conservation principles to be able to solve stuff. And then you're gonna consider how the way you perceive things might not be the same way I perceive things based on the physics that I've had some experience with. And this really depends on whether you're including or not including friction, whether you're treating it as an open or closed system, changes our perspective on stuff. All right, let's get started. So I was talking about this ski lift you guys are working on. Well, we are part of an engineering firm now, and we're designing the RJUHSD Mountain ski lift, which is awesome because we just got some new snow up here. We've got 3 possible routes up the mountain. They all go to the exact same spot, but one of them is nice and shallow, one's pretty steep, and then one is really, really, really like double black steep, which is my favorite, of course. You guys are gonna have to help me figure out which one's the cheapest to build, which one's the easiest to operate, which one gets skiers to the top the fastest, which one's the safest, and anything else we wanna get going on here. So let's kind of visualize these. You can see that in all 3 cases, we're going to the top of the mountain. It is the exact same height up to the top, no matter which route we take. The height stays the same. But obviously there's a shallow, medium, and steep way to get there. Now, again, we want to make this thing affordable. Money is an issue, so we want to make sure that we're not paying for too much steel cable, not too many poles, not too many lifts. We want to build something that's, fewest parts equals cheaper. We also don't want to pay for ongoing energy costs. Electricity is very expensive. And then, of course, we also want to make sure it's safe. So those are the requirements for what we're doing. All right, so let's take a look at some free body diagrams and some forces. Now let's say you're lifting something up a hill. There it is. That could be a skier, that could be somebody on a snowmobile, it doesn't matter. What we want to do is we want them to move up the hill at a constant velocity. We don't care how fast they're going, we just want to give them enough force to maintain their speed in each case. So we're looking for when the net force is all add up to 0. Now, in each case, this object, no matter which route we take, is made of the same mass, is affected by Earth's gravitational field the same way, and therefore is going to have identical force due to gravity, which we more commonly refer to as weight. And keep in mind, too, that regardless of the slope, gravity points straight down towards the center of Earth. The slope doesn't affect which way gravity points. However, the normal force, the supporting force from the surface, always perpendicular to the surface, is going to get affected by which way the hill is sloped. So perpendicular to those 3 different slopes is a different direction. That can affect things. And however much the surface isn't supporting that block, the cable tension is going to have to pick up the rest. And the cable tension is going to be dragging them from left to right here. So let's start to add this in. First up, we're going to start with gravity. Yep, point straight down, all 3 objects exactly the same. Next up, I want to consider, compared to the slope, is gravity more perpendicular to the slope or more parallel to the slope? So I'm going to put in these dotted lines showing the components of those vectors compared to the slope. And it looks like in the first one, the shallowest one, that gravity's, almost straight down. Whereas in the third one, the steepest one, gravity is equal parts, pushing it, downhill on the slope, but also into the slope. Both of those two different vectors. Now that we thought this through, we know that the slope is going to provide supporting force in the direction that's perpendicular to gravity. So quick question for you. Which of these versions gets the most support from the surface? And if you pick the shallowest one, you are correct. As the slope is less and less lined up against gravity, it's providing less and less support, which means that we're relying on more and more cable tension. So in the steepest slope, the cable is indeed pulling the hardest to get them up that slope. But wait, there's more. So here's that same picture of the slope. Here the engineers went ahead and ran us some numbers. The mountain is exactly 500 meters high. Whether you get there with the shallow, medium, or steep slope, you get to the top of the mountain. You can go from the bottom of the mountain to the top of the mountain the steep way, the shallow way, the medium way, it doesn't matter. You're still ending up at the top of the mountain. That is the same. However, which hypotenuse of those three triangles is the longest? It's definitely the one with the shallowest slope. You guys can see how long that is. So if we have less cable tension, less force, which we just previously identified, but we do it across a longer distance, versus if we have a really high cable tension, like in the steep example, but we do it over a very short distance, how does that affect the energy required to move the skier up to the top of the mountain? Now, you could be thinking one of two things, and let's get our handy dandy equations up here. You could be thinking, top of the mountain, I'm hearing that they're high up. Let's just talk about potential energy. The skier, whatever their mass is, doesn't matter, is going to go up the same height no matter which route we lift them up. So the potential energy they end up with is exactly the same. The other thing you could be thinking of is that work done by the ski lift motor onto the skier, that depends on the multiple of force times distance. So for the shallow example, we're picking a really, really, really big distance times a fairly small amount of force from the ski lift cable. Or we could pick the opposite. We could pick the really steep slope where you have to have a ton of force, but you can apply it over a very short distance and be done. And in both those cases, let's see what the work comes out to. I already did this math for you guys. Well, let's see. 2,500,000, blah, blah, blah. All three cases, right? Are those numbers, first of all, the same or are they different? Some of you guys might be thinking, oh look, the steepest slope is the biggest number. No, 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 no. Those aren't significant figures. We should be rounding. We should be rounding all three of those to 4 digits effectively. So you should be saying all three of those numbers are 510,000-ish. They're all basically the same thing. The rest of those values on the end there, those are just rounding issues. You guys know there's no such thing as a perfect measurement. There's always a margin of error. You've experienced this in your labs. And so that's something to not even worry about. Those are all the exact same energy value. And we could have figured that out either from the work equation or from the potential energy equation. It doesn't matter which route you get. If you end up on the top of the mountain, you end up with a certain amount of energy. It doesn't matter how you got that energy. You could take an elevator to the top, straight up, and you'd still be provided the same amount of energy. Or you could take like one of those big snow groomer machines up to the top. And although the snow groomer had to lift itself to the top and it burnt a ton of energy doing that, the energy provided to you is still exactly the same. So it doesn't matter which route you take. In all cases, you end up 500 meters up the hill. All right, now let's check out some forces here. First of all, we got the same 3 skiers. And now we're thinking of, okay, let's say we're coming back down the mountain. Now in your guys' head, which one of these, if there is friction, if there is air resistance, if it's totally realistic, which of these is the skier going to end up going the fastest on if they just point straight down the mountain and go? And I think we can all agree that it would be the steepest one that ends up the fastest. But here's a weird question. What if there isn't friction and there isn't air resistance? In this case, they all started with the same amount of potential energy at the top. Who gets more kinetic energy by the time they get to the bottom? And hopefully you're thinking, energy is a conserved property. However much energy they start with should be the same amount of energy they end with, assuming the system is closed, assuming that energy can't leak out of the skier and get spread out all over the snow and the skis and the air as thermal energy. If that's true, then they all have to end up with the same amount of kinetic energy at the bottom, which means that regardless of which way they went downhill, in the absence of friction, in the absence of air drag, they all will go exactly the same speed. Now you might be thinking, okay, but that's not realistic. There is friction, there is air drag. This is an open system. No system is perfectly closed because entropy, the saddest idea in the world, that energy tends to go from organized to disorganized and spread out and be less and less useful throughout that process. So let's pop up, first of all, force due to gravity. Can you predict the next step? We're going to put some dotted lines on there, make sure we know the component vectors. Next step after this, going to be normal force, making sure that we're not sinking into the slope or jumping out of the slope. That should be all equalized so that we're not moving on that axis. And in this case, who gets the most normal force? It's the one on the shallowest slope. And what we're worried about right now is friction. So go ahead and take a look at your equations. I put up some from Unit 1B as well up there. Hopefully you guys can spot the friction equation. The more normal force you get, the more friction you get. So who's experiencing the most friction? Again, the one on the shallowest slope is experiencing the most friction. It's going to be slowing them down. And is it slowing them down for a short time or a long time? It's slowing them down for a long time, and more importantly, over a long distance. The force of friction is going to be biggest for the shallowest slope, and they're also covering the largest distance while friction is acting against them. So force times distance is work. Work is a transfer of energy. Is the friction transferring energy into or out of the skier? It's transferring it out of the skier. We'd call that negative work done. They're losing energy because of friction. It's spreading out to the environment. Entropy converts it into thermal form. So in this case, they all started with the same amount of potential energy. But if this is an open system where we do care about friction, then the skier going down the shallowest slope is going to lose the most energy through work output. And they're going to end up with very little energy left over in kinetic form, which matches our realistic expectation that if they're going the slowest, they must have the least kinetic energy in that scenario. Somebody going down the much steeper slope is experiencing slightly less friction because of the way those vectors line up. They're experiencing it over a substantially smaller and shorter distance, and that means less energy is transferred out of them. They retain more of that initial potential energy in kinetic form. At this point, it might be really good to pause the video and make a lull diagram, one of those energy bar charts, tracking before and after they go down the slope. I would do it in both open and closed system thinking. So I would recommend that you guys grab some scratch paper, pause the video right now, and make an example where without friction, how does the potential energy turn into kinetic energy? And with friction, how does the potential energy turn into both kinetic and thermal energy, which you could track as leaving the system through work or heat if you'd like to, and compare and contrast those different examples. All right, that is about it. What I need you guys to do next is make sure you're following the instructions on Google Classroom. There is a Google Groups discussion board. I want you guys to finish the Unit 4 Handout 5 ski lift activity. Carefully go through each of those problems. Some of them are pretty tricky, but if you keep energy conservation in mind, and you can clearly distinguish between whether the question is asking about open or closed systems, you should be all right. Then you'll go online on the forum. You'll post your recommendation for the best of the 3 ski hill slopes to actually go build out. And then you'll also go and check your work on that handout, and then post something you probably got wrong or something you were confused about, as well as, in both cases, respond to 2 of your peers' discussion posts. Last up, I'm going to have office hours every day. Those times are posted in Google Classroom. We're going to be using Zoom as a platform, at least at first here. I may also experiment around with Twitch or Google Hangouts and see if any of those is better, but I think Zoom is the way to go. And I hope you guys can access all of this. Let me know later today if you have any questions. And yeah, good luck, have fun, and try to stay warm. I'm going to start on those ski lifts.